Um, so thank you for still being around after, a long week of lots of, very intense lectures and tutorials and all kinds of things. So this should be a little bit on the light affair side today, I hope. So yeah, just to make you happy again so you can follow along. Just to briefly recap what we did at the second half yesterday, I talked about driven interfaces, gave you two different motivations for the Cardy-Parisi-Sung equation, which is, the canonical universality class to describe growing surfaces and driven interfaces if it's in a nonlinear growth regime. It's of course the linear version too, which is just a noisy diffusion or Edwards-Wilkinson equation. So in kind of a rescaled, my favorite rescaled manner, the KPZ equation looks like this. We have a time dependence of this kind of height field, which is a coarse-grained, height field, not too fine-grained, because then you have overhangs and the like. And we have competition between three things. We have some kind of random forcing, which in the interface picture could be just random deposition of particles on the surface. Then we have a smoothing term, which looks diffusive, because once the particles have reached the surface, all they can do is move about. And then we have this term, which kind of favors already local inhomogeneities to grow faster than smoother areas of the surface. Or make the interface growth move faster in regions where you have some spatial inhomogeneities. So that's the nonlinear term. Again, when this is gone, this is the Edwards-Wilkinson equation. When it's there, it's the KPZ equation. And we just assume uncorrelated white noise. And what I've done here is, because you can always do that, as I was arguing, setting KT to 1 or something like that, which isn't here anyhow, it's a non-equilibrium problem, but I can formally write the noise term, noise strength in the shape of an Einstein relation, because I can just do it, right? And then I was telling you that there is two very different dimensional regimes for this equation. One is in less than 2 dimensions. In less than 2 dimensions, the surface displays generic scale invariance. Generic scale invariance with non-trivial exponents. But you can fix them in 1 dimension because the system is equivalent to, in 1 dimension, to other systems that are very well known and studied. It's the Burgers equation for equivalently driven diffusive systems. Those are all the same in 1 dimension, so that's kind of cute. In the Burgers equation, which is an equilibrium system, we know that the stationary canonical distribution is just e to the minus kinetic energy. So 1/2 u squared. But u in the translation between Burgers and KPZ equation is just the gradient of the height field. So we know that in the 1-dimensional KPZ equation, this is our stationary distribution. Well, this is a non-equilibrium steady state, so that's quite amazing. So we have that. If you look at that, we already see this is Gaussian. So in my terminology for scaling exponents, eta is 0. Right? So if eta is 0, I know, eta in the business of growing interfaces is usually written in terms of this roughness exponent, chi. If eta is 0, we're in 1 dimension, this is 1/2. So we know that already. Then we have this general scaling relation, which applies when g is non-zero. So we know z is 3/2. Or equivalently, we knew that from the Burgers or driven diffusive systems. So we know the scaling exponents, which is nice. And as I told you, there's a big industry and really fantastic new results on computing scaling functions, which are highly non-trivial in 1 dimension. The Tarzeb or equivalent to the KPZ equation. A really different scenario happens in more than 2 dimensions. So 2 dimensions is really a lower critical dimension for the, it's called non-equilibrium roughening transition. If I'm in more than 2 dimensions, it depends on the strength of the nonlinearity in these units. So kind of D is already scaled out, and D measures both, in this situation, the smoothing effect and the noise. So in this kind of effective coupling G, if we're less than some critical value, the surface and long length scale just becomes smooth and flat and is happily described by the scaling exponents of the Edwards-Wilkinson equation. If I'm beyond that critical coupling strength, the system becomes very rough. And at least perturbatively, we don't know how to treat it. Of course, you can simulate it. I told you there are non-perturbative, semi-analytic numerical methods to deal with this. but that's a very intriguing problem. So there is even a non-equilibrium phase transition in the system that separates two different generic scale invariant regimes. One with mean field exponents and one with certainly not mean field exponents. And it turns out that at the roughening transition, you magically can again fix the scaling exponents. They're just marginal. So the roughness exponent is 0, dynamic exponent is 2. And you can also figure out other things like nu and the effective correlation length exponent. So that's the fundamental scenario for the KPZ equation. Are there questions? I'm always scared when you say elementary is 0. Yes, so this is basically using this term. You're right. That's right. That's where that's hidden. The actual argument for that, of course, make that clean. You do an RG analysis and you look at the fixed point structure, but yeah. After you know that's fine, you can come up. Yes. Actually, I like in that sense, the Galilei, tilde invariance argument is better because it's cleaner, it's less input, and so I was giving both of these. Yeah. But I think historically, the one that we just mentioned is the first. People are very intelligent, can get the physics right, and without doing the math. Normally it's the other way around. You do a long calculation first, and then at the end you come up with easy arguments why that works once you understood the system. Which means you actually understood the system once you can come up with easy arguments afterwards. Okay, other questions? All right, before I turn to this issue, let me just briefly complete this because there are two variants of the KPZ equation that are called conserved KPZ. Yeah, it's kind of a funny name, but it comes from the terminology that we've been using in these lectures too. So as we went from model A with a non-conserved order parameter to model B with conserved order parameter, you can essentially by saying instead of just direct relaxation, you have to have diffusive relaxation, you could look at that for the KPZ equation too. So what people have argued, well, I really have surface reconstruction. What I should do is maybe I should add minus Laplacian here on top, right? Then you have additional kind of really just purely diffusive relaxation. Then you still have a choice because this is not an equilibrium system. I can either demand that my noise satisfies this, is conserved in the way I was describing it before. So I would put a negative Laplacian here too. But it's a non-equilibrium system. I could still have just random deposition, which doesn't satisfy that. So there are two versions of that. In my earlier language, where A is either 0 or 2. So A is equal to 0, A is equal to 2 are the two cases we're going to look at for this conserved variant. If A is 2, if A is 0, this is called the Wolf-Villin model. And is meant to really describe molecular beam epitaxy because you just have random deposition of particles, but then you have diffusive relaxation with on this interface. So that's the Wolf-Villin model. For A equals 2, this is called the Cern-Grant model. Okay. So you can study that. It's not too hard to do, straightforward. So let me just tell you what the results are qualitatively, because they turn out to be quite different to this. In neither of these variants, you get a roughening transition. In all these variants you get is just pure scale invariance. So it's always this scenario that extends, however, to higher dimensions. So in both these situations, we just have generic scale invariance, no roughening transition. It turns out that you have an upper critical dimension in the sense beyond that is mean field theory, below that it's non-trivial exponent. That turns out to be 4 minus A. So 4 in this situation, 2 in this one. You can derive scaling relations. You may not be surprised to see that in this language C is 4 minus eta. That's precisely as in model B. And you have that chi is 4 minus A minus D minus eta over 2. So there is some version of C plus chi is 2, but it involves dimension and 2 etas and things like that. So that's how that looks. And so that means there really is one independent exponent eta to compute here, and everything else is fixed, and you can do that. And it turns out that the lowest order in an expansion about this upper critical dimension, eta is epsilon over 3 in both cases, but it's different epsilons. Because it's 2 minus d in one case, and it's 4 minus d in the other case. But that's not so important. What's really important here is that this additional conservation law eliminates this roughening transition somehow. Can I give you a simple argument staring at the equation why that is the case? No, I would love to. Okay? It's one of the non-trivial things to look at these non-linear stochastic PDEs and be able to even stare at them and find out what, if you like, the phase diagram might be. And it's it's not a trivial issue. So it's not clear what this generic scenario is. The roughening transition, is this really a special case for that equation, or is it more generic? We really don't know. To have conserved noise, the nonlinear term, it's still preferential growth of where you have, kind of spatial inhomogeneities already. That's not going away. So this is just, it's relaxing fast, it's relaxing diffusively all over. Best I can say about that. Okay, so in this final part of this series, I'd like to discuss scale invariants and phase transitions in reaction diffusion systems. So that very nicely ties into things that Sid has explained to us on Wednesday afternoon and yesterday afternoon. So I can happily make some contact to that. But I'm going to look at that as, to say, reaction diffusion system in spatial context. It's still a little odd to be standing here because pretty much everything I learned about these systems, I learned from reading Sid's papers and from John Cardy, whose postdoc I was at the time, he introduced me to this field. But, nevertheless, all right. So what I mean with chemical reactions, it's not really chemistry necessarily. It's when you have processes, which are going to treat as stochastic processes, where particles change identity. So which is what you would have in chemical reactions. The chemical species are transformed into each other, so they change identity, if you like. It could, of course, be particles in particle physics. It could be nuclear physics. You still have reactions. And even more importantly, sometimes you could have effective degrees of freedom in physics or condensed matter physics that you describe in this particle language. And Sid gave us a beautiful example already on Wednesday, when he looked at the domain walls in an Ising chain and argued those are the actual, the really important dynamical degrees of freedom. And it's actually sometimes better to think of these domain walls particles as the relevant degrees of freedom in the system rather than the individual spins. So those are really the quasi-particles you'd like to think about. I was going to explain that in some detail, but I don't need to do this because Sid has done that. I don't need to repeat that. So if you think of an Ising chain, domain walls are point-like particles, and they undergo reactions such as spontaneous creation, if you're at finite temperature, that goes away at 0 temperature. And then you have pair annihilation. 2 domain walls can just annihilate, which is, aside from diffusion, which is, spin flips, where domain wall just moves right or left, is the only process that survives at 0 temperature. So at 0 temperature, this becomes an irreversible process of just pair annihilation and diffusion. And that's kind of the first example we're going to look at. Actually, slightly generalizing this, we're going to look at irreversible annihilation or coagulation for a single species. And I'm just going to write down Ka goes to La with some rate lambda k. So that's a probability per unit time. And I treat that as a stochastic process, where I want that L could be 0, but it's definitely less than K, because otherwise things wouldn't be happening. If L were larger than K, would have production, and I'm not going to look at that now. Okay? So the first thing that you always want to do is, of course, get a feeling of what's going on. You do this on the level of a mean field rate equation. Again, Sid has nicely explained those to us already, so we can just take over there. equation. So let me emphasize again what the background of this is. Of course, you write down what you really want to solve to fully treat the stochastic process. You would write down a master equation for the probabilities, configurational probabilities. In this case, the configurational probabilities are given by the number of particles A at any given position X at time T. This is a spatial system. Okay? Now that's a complex system, and so we are going to shirk this first and just think of the moments. The first moment of that would be the particle density. So I'm going to look at the particle density, which I'm going to call A of t. What is this? This A of t here would have to be some spatial average over a local particle density, A of x and t, and likewise for higher moments. But of course, what happens here really is I need to have k particles come together at the same time and the same point or anywhere close in the vicinity for this reaction to happen. So I really need to understand a kth order correlation, right? So that's, of course, you can write this down in your master equations, but if you write down the kth order correlation, you run into the standard hierarchy issues. If you want to write down a equation of motion for this thing, it involves higher correlations and lower correlations, and you need all these. And you don't get a terminating sequence of that. So the most brutal way of dealing with this is the mass action or mean field factorization, where you just claim, well, let's assume we have a well-mixed system. Which, as Sid was arguing, often happens in industrial reactors because there people carefully stir the system. And so any kind of spatial correlations that might show up are destroyed by an explicit interference with the system, right? So if you have a well-mixed system, then this kth order correlation factorizes just in the density at the first moment to the power k. So we can kind of write down a to the k and replace that by that to the k, which really means if I looked at connected correlation functions, which is kind of a difference of that, I ignore fluctuations there and set that to 0. So what this rate equation or mass action factorization is assuming is that you neglect spatial and actually also temporal correlations. Okay, so this may work well in industrial reactors. It does not work so well if you think about surface reactions because you don't tend to stir things on the surface so much. Also, we'll see there is critical dimensions associated with that. So this is a fine approximation as far as power law exponents are concerned in sufficiently high dimensions, but not in low dimensions. And it does not tend to work so well in many biochemistry or biology applications because there you're in a crowded environment. Things can't actually mix that well, and correlations can build up, and they're actually sometimes crucial for biological functionality. So I personally think one really needs to worry very much about spatial and temporal correlations in biological systems, and that is actually a field where physicists can contribute much. Statistical physicists, specifically with expertise in non-equilibrium physics, can contribute considerably to quantitative biology. Okay, after these philosophical statements, let's write down the mean field rate equations for this system. So I want to do dA of t by dt. All I have is particle decay. So I'm never gaining density here. All I can do is lose, and I lose essentially with this rate lambda k, maybe with a factor k minus L in front, which I don't want to care about. And then I do this mean field factorization. So I'm just closing this by brute force by saying, this should be a kth order correlation function, but I just replace it by the mean to the power k. So let me maybe emphasize that this could be a brutal approximation. Well, now it's closed and we can integrate it. So let's first look at the obvious case where k is 1, and therefore L has to be 0. So that's just decay. It's A going to 0 as we're writing it. Really, that means the particles may not disappear, they may just go to some inert state that doesn't participate in reactions anymore. Okay. Whatever that is. So this would be A to 0, which could be going away and it could just be an inert state. That is, however, not retrievable. So we have an absorbing state and things don't change. Then this is radioactive decay, and the solution of this thing, of course, is just exponential time decay. It turns out that in that situation, of course, there's no binary things involved. This isn't even an approximation. It works just fine. Same thing you would get from the master equation. So interesting case is when k is larger than 2. And so L is 0 or positive, but less than k. Then we just need to integrate this thing. And so what we get are separate variables. So the a is here, dt on this side. I get lambda k times t. I get a minus sign, and I need to integrate from 0 to time t. And I need to do dA divided by a to the k. Right? So k is larger than 1, which is why I took care of this first. And so this is a to the minus k, so I'm going to get a to the 1 minus k divided by 1 minus k. I'm absorbing the minus sign in the divided by 1 minus k and call it 1 over k minus 1. And then at the upper limit, I get 8 to the 1 minus k, and then minus the initial density to the 1 minus k. Now I can solve for 8 of t. And that's going to be, need to throw this on this side, multiply through with k to the minus 1. Invert and take the 1 over k minus 1 power of that. So I get an algebraic decay, especially if I look at large times. Large means compared to essentially 1 over lambda k. K minus 1 is of order 1. And then the density a naught to the k minus 1. So if I look at times much larger than this, I can forget that first part. And this goes as 1 over lambda k to the t to the power 1 over k minus 1. So decays algebraically, not exponentially. Okay? And you see if k is 2, so if I have pair annihilation, I get a 1 over t decay. If I have triplet annihilation, I get 1 over t to the 1/2, and so on and so forth. That's the mean field statement. Now, if you see power laws coming out of a mean field theory, you have to worry, because power laws tells you there's scale invariance. There's scale invariance, there's no reason not to have fluctuations on arbitrary scales. So fluctuations might modify even the power law answer drastically in sufficiently low dimensions. So we have to worry about that. Okay, you don't have to worry about that so much once you have exponential decay, because that tells you finite time scale. If this is diffusive propagation, finite time scale translates to finite length scale. So, fluctuations are controlled by finite regimes. So let's look at more carefully what actually happens at diffusion limited annihilation. So now I'm going to really worry about spatial effects and spatial correlations. And we're going to do this for the pair annihilation. Actually, again, call lambda 2 lambda, because I'm going to be too lazy to write down that index. Sid has kind of alluded to how you would treat this effectively. And actually, historically, it's a very famous paper by Smoluchowski from the earliest 20th century, 1913 or so, I believe, where he analyzed that carefully. And he did precisely the story that Sid was telling us. There's a reaction radius if you do continuum. And you try to find out the diffusion flux of any other particle. Or you have two particles, and you do the relative diffusion flux as you hit this reaction radius surface. you compute the flux on the surface, and you call that reaction rate, and it takes all kinds of anomalous behavior. Works out very nicely, but I'm going to not even do that. I'm just going to give you a scaling argument of what might happen. And before we do that scaling argument, let's draw a picture and figure out what the physics is. So here's that picture. I have particles, and I'm going to look at those on a chain, on a one-dimensional line. And they have some random spatial distribution on that line. So they're not uniformly spaced, they're also not clustered on one side. Some generic Poissonian distribution. And so these guys are doing nearest neighbor random walks, and they hop about happily until they hit each other, and then they react with some probability per unit time, lambda. Right? So close by, particles like this, as they move about, have a good chance to die. They take each other out. Likewise, these things take each other out. So initially, the probability for reactions is just given, is really dominated by this reaction rate. And I'm initially in some reaction limited regime. Things happen, if things happen for abundant density, that's really controlled by the reaction rate. There's only one type of particles. We get to the two type of particles next. Here we have one type of particles. Single species, single species. Okay, now you imagine this has gone for a while, and we end up in a dilute regime because any kind of unhappy close neighbors have killed each other. And so once I'm in that dilute regime, what happens? These surviving particles will have to be fairly distantly spaced from each other. That's the property of the survivors. So what the system does under these reactions, it's building up spatial correlations, more precisely spatial anti-correlations. Actually, formally, you can actually map that to fermions in some sense. All right. So there are spatial anti-correlations. Which is actually the physics behind the kind of anomalous behavior you find in this reaction surface calculation, which I also do recommend you to have a look at. So you get spatial anti-correlations. At this point, the dominating time scale for any further reaction to happen is not the reaction rate. It is the diffusion rate for these guys to come together and meet. And so how is that described? Well, if they are at a typical separation scale L, I need to relate this separation scale L to the characteristic diffusive time scale, which is square root of 2 dt. So it'll take them a time of order square root of t to find each other if they're separated by distance L. And then, they have a good chance to react. But that is setting the time scale. It's the diffusivity, not the reaction rate. So we entered what, here things were initially, they were reaction limited for large density. Low density things become diffusion limited. Well, this is our characteristic length scale. These particles, aside from factors of order 1, will all be spaced apart from each other by LD. So what's their density? It's 1 over LD to the power dimension. So we would argue that the density of these things should just be of this form in d dimensions. And so this goes as diffusivity times t to the power d over 2. And then you see in dimensions less than 2, that is 1, this is slower because it's 1 over square root of time. It's slower than the mean field 1 over time decay. So rate equation here tells us, I forgot to say that, I did say it, but I didn't write it down, that A of t goes as 1 over lambda t. But this diffusion limited regime, it only goes as 1 over diffusivity times t. Lambda becomes kind of irrelevant to the square root of t. Much slower decay. So you get a drastic change owing to these spatial anti-correlations in the density decay. If you think I was just waving my hands too much to give you the square root in one dimension, I can happily refer back to what Sid told us on Wednesday, because he actually computed that, but he computed that in the magnetization language and for coarsening of an Ising magnet at 0 temperature. Because, as he was saying, at 0 temperature, all we have is this process and diffusion. And if I think of the domain walls, and the magnetization decay just directly translates into this particle decay. So he gave us the exact solution, and this 1 over square root of time there comes from some kind of Bessel function, asymptotic analysis. So all fits nicely. And then you can also devise, and that was done by Piliti and then also by Ben Fulmeyer-Lee and John Cardy and so on, a renormalization group approach for this that recovers that and actually kind of justifies what happens in the Smoluchowski approach. So if I want to write down a more or less complete picture of what happens is, as function of dimension, if I'm in dimensions larger than 2, this is a faster decay than the rate equation decay, so diffusion limitation is not an issue. And that has to do with the fact that if you're in more than 2 dimensions, random walks are nicely mixing. It is only in dimensions 2 and less that you carve out these empty zones, depletion zones. So 2 is an upper critical dimension. And the basic physics here is carving out these depletion zones. And you carve them out permanently because of the recurrence probabilities of random walkers. In higher dimensions, you carve out some depletion zone, but other particles come by and happily fill that space. So if I'm in more than 2 dimensions, I just get 1 over lambda t. If I'm in less than 2 dimensions, so physically it's 1, I get 1 over square root of dt. 2. If you write at the critical dimension, you get the mean field behavior, but not the direction rate, but the diffusion rate, and you get a log correction, which turns out to be just log dt. So a little slower. Mean field and then logarithmic corrections to that. You can analyze kind of scaling behavior of these rates, how they depend on density and the like. You can convince yourself that for the kth order annihilation that I was looking at here, the critical dimension turns out to be 2 over k minus 1. So if I have pair annihilation, I get 2. If I have triplet annihilation, the critical dimension already is 1. Okay, so only in 1 dimension do I need to worry about fluctuation and correlation effects there, and they're just logarithmic. So if I do k equals 3, therefore, what you get is that a of t goes like 1 over lambda t. Now if you stare back at here, k equals 3, this is 1/2. So it goes down as 1 over the square root of t in more than 1 dimension, and it goes as field result with logarithmic corrections and all that to the power 1/2 in 1 dimension. For higher order processes, lambda 4, 4th order annihilation and the like, the mean field power laws are just fine in any physical dimension. Okay, so this is the story about pair annihilation of identical particles. Questions? All right, and let's come back to your question and look at 2 different particles, so 2 species pair annihilation. That's a richer system. And when you see that first, or anyhow, when I saw that first, I was kind of stunned by the fact that it's a much richer system because it looks almost identical, right? Because what you write down if you have 2 species pair annihilation, you just say there's 2 species A plus B, and on encounter these unhappy particles annihilate. So there could be particle-antiparticle annihilation. So if you look at that, that looks very similar to a plus a to 0. The crucial difference to a plus a to 0 is not what happens. It is what does not happen. And that's kind of implicit and not explicit. What's not happening is the A's are good friends to each other and just ignore each other, and the B's are good friends to each other and ignore each other. There's no reactions between the A's and B's, and that is the crucial difference. The second crucial difference is that in this business, there's a conservation law. If I look at the even local concentration difference of A and B, right, even on a lattice side, even in discrete steps, whenever I'm killing an A particle, I'm also killing a B particle. So the difference in these concentrations never changes. The concentrations change, but the difference doesn't. So I'm going to call this C of x and t, and that thing is conserved. It's strictly conserved in the stochastic process, not even under any kind of mean field assumption. That's the second crucial ingredient. Before we look at spatiotemporal correlations and the like, let's look at the rate equation. Rate equation says, well, I look at change of A. And how is the density of A particles going to change? Well, it's going to change whenever A's meet B's, but we just said in the mass action factorization, that's just the product of densities of A particles and the density of B particles. Really, again, that should be a two-point function, but we just brutally factorize that. And of course, that is also the change of B particles with time, density. All right. So we need to distinguish, it turns out, and you'll see why that is in a second, two cases. The first one is the initial density difference is positive, non-zero. So I have a majority species, and I decide to call them A. I could call them B and turn this around, doesn't matter. Okay? So we have a non-zero density excess initially of the A particles over the B particles. So what's going to happen? As I go to very large times, I'm going to kill off all my B particles. But there will be A particles left. So this is going to go to a finite positive number. What is that positive number? Well, it's going to be C0, because this, by conservation, is also that difference. This is 0. Right? Well, then I can go back into these rate equations and stare at the equations of B at sufficiently long times when essentially the A's have reached this limit and there's very few B's left. Once the A's have reached this limit, C0, that's a constant, and I just look at essentially a radioactive decay equation for the B particles where the effective decay rate is lambda times C0. So at large times, I would get e to the minus lambda C0 t, an exponential decay to 0 for the B density. Well, that of course will be the same behavior for the difference of the A density to this asymptotic value. You just plug a correction to this in here, and you get that constant, and you get that same behavior. So this is also A of t minus A infinity, which is C0. So both of these will just decay exponentially. Oh, I'm treating a, so I'm always talking about a continuum and thermodynamic limit where I hold the initial density and things like that fixed, but not a finite number. If I have to worry about finite numbers, then you have to worry more about the discreteness and something else. So let's think about this kind of scaling limit. Otherwise, there's no sense for exponentials. Right? At some point, you have two particles, one particle, end of story. Oh, I'm not convinced either, fundamentally. However, the critical dimension that tells me if these correlations are important, at least for the power laws, not for the prefactors and scaling functions, but for the power laws, tells me that if k is larger than 2, I really don't need to worry. So A posteriori, it's fine. A priori, it's extremely questionable. Okay? But again, this is only about power loss. That does not mean that the other predictions you get from the rate equations are fine. Quantitatively, you could still be badly off. Right? It's just that the power laws have changed. So all good questions. Others? Right, so that's the mean field story for this one. Now let's just stay with this situation here and think about, refined physics in terms of what we just learned for A plus A to 0, which is the carving out of depletion zones. You still have the depletion zone physics in this business too. Any A's and B's that are initially close to each other will annihilate, and the survivors will have spatial anti-correlations. If I'm in less than 2 dimensions, because it's again the same kind of diffusion argument and recurrence of random walkers argument. So I can kind of almost guess what the answer is. If I'm in less than 2 dimensions, I really need to take into account depletion zone physics. So let me write this in terms of the logs of these densities. And then what I would have above the critical dimension, I would get exponential decay as we just had. So the log goes as minus lambda c naught t. If I'm in less than 2 dimensions, specifically in 1 dimension, I would expect that this t, as it was here, the 1 over t was replaced by 1 over square root of t. And so we would expect essentially the same substitution, and that turns out to be correct. So what I really should have is dt, maybe c naught in there 2, to the power d over 2. So that's stretched exponential decay. It's slower because I'm carving out this depletion zones, but it's exponential, but with 1 over square e to the minus square root of t. And then at the critical dimension, for depletion zones, I would get log correction to the mean field behavior, so something like minus dt over log dt. So a slight refinement of what mean field theory tells us. Okay, so that's the case of some initial majority density. But you see something funny has to happen as I send C naught to 0 because that exponential goes away. So C naught plays the role almost of a critical parameter in this. And as the exponential goes away, maybe there's some kind of power loss showing up. So let's analyze the special situation where this density excess, difference of A naught and B naught, initially is precisely 0. So if I then look at the rate equations, which is happily still there, really I get the same behavior as there, so I would expect the 1 over t. Because now, with the initial conditions equal, and the equations of motion equal, I'm basically back to this scenario. So the integration of this just gives you this behavior, and so asymptotically this goes as 1 over lambda t. Precisely as here, which was the A plus A to 0 result. So indeed I get algebraic decay, even within the mean field approximation, and that just signals the special kind of critical situation you have as you send that parameter C naught to 0. That was the mean field answer. So let's see what happens if I worry about spatial correlations. And to worry about spatial correlations, the crucial bit is to take into account that this local density C of x and t is conserved. So it needs to satisfy a diffusion equation without noise. That we know needs to be satisfied by this quantity C. So by that we can solve for arbitrary initial conditions. We can solve this by Green's function. All we need is the diffusive Green's function. And then once we have that, we know the particle density, not the particle, this concentration density C of x in t as function of time by integrating in d dimensions over the Green's function and the initial density at time 0. Right? This Green's function then will have to satisfy the diffusion equation, and it needs to have the property that at time equals 0, this is a delta function. Usual Green's function properties. Well, you know that, because that is precisely the solution of the diffusion equation that everyone tells you. You start with all the particles at the same position, and then you let them diffuse about. That's the standard Gaussian that you just write down, so we know that Green's function. You do this in Fourier space, invert back, and so on and so forth. I'm sure you've seen this. You do it in one dimension, then you treat all Cartesian coordinates as independent, so you just take the dth power. It's going to be 4 pi dt, d over 2, and then a Gaussian vector x squared over dt. And that has the right properties, satisfies the diffusion equation, and at time 0, this becomes a delta function. Okay, I assume you were. So great. So we want to do essentially a statistical average later over typical initial conditions, so some random initial distributions of A and B particles. And so I'm going to do an average over initial conditions, and I'm going to indicate that with this overbar. So what's the initial density of A particles? I'm just going to call that A naught. What's the initial density averaged over all kinds, even not averaged over all kinds of initial conditions? The density is just the same as for the B particles. That was our assumption, we have the same densities. I'm assuming a Poisson distribution initially, right? So randomly placed both A and B particles, so I can even write down the correlations at different positions x and x prime and look at the second moment. What is this going to be? Well, it's going to be A naught square if x and x prime are not the same, or actually this difference is the variance, and the variance is a Poisson distribution, so the variance is just going to be E naught, it's equal to the mean. It's going to be equal to the mean if x is the same as x prime. If we are talking of different positions, these are statistically independent variables, so it would be 0, and so this needs to come with a delta. Notice that units are kind of fine because the A's were densities. That's a density squared. This has inverse volume units, so it's a density 2. And of course, that's the same as the B correlations. By symmetry. And you write it in this form again, then it's the same. Otherwise, I'd have to subtract A naught squared here too. Okay. So with this, we can, and then we need the AB cross correlations. Well, that's just going to be A naught squared, because we are treating the A's and B's as statistically independent particles, and so there is no term like this in these cross correlations. Right. With this, I can infer the properties with respect to averaging over initial conditions for this field C naught. So I can look at C of x and 0, and of course that's 0, because it's the difference of A's and B's and they have the same average. I can look at C of x 0, C of x prime and 0. Do this average. So I just need to plug in. C is A minus B. So I'm getting A of x prime, which is this stuff, then I'm getting minus b of x times minus b of x prime, so that's b prime, same story, so I just get this twice. Then I need to subtract a of x times b of x prime, and a of x prime times b of x, so I need to subtract twice this value. And so that just cancels, and this thing is just proportional to this delta function. With this, we can do a quick calculation and figure out what c of x and t will be if I first square that, because that one is just going to be 0. So I'm squaring this, which means I write this thing down twice, and then take the average over initial conditions, which I can do because the initial densities are sitting here. And I know the second moment for this. Right? So I need to write this down twice, which means I have two integrals, both of which involve this Green's function at the same time, but of course at different positions. X minus x double prime and t. And then I get c of x naught, c of x prime 0. And I need to do this average. That average we just figured out was twice a naught, delta of x minus x prime, which is x prime minus x double prime. Because this was c of x prime 0 and c of x double prime 0. So that's very kind, because that delta function gets me rid of one of these integrals. So this is going to be twice a naught integral over x prime. And as x double prime becomes equal to x prime, it's just the square of the Green's function. Well, the square of the Green's function I can handle. This is 4 pi dt to the power d, because I just squared it. And then in here, e to the minus x prime squared divided by twice dt. Not 4 because I squared it. All right, that's a Gaussian integral. We can do it. Right? This is going to be square root of 2 pi dt to the power d. Okay, and then I can collect these two terms, and I'm finding twice a naught divided by 8 pi dt. And you see I have a d over 2 upstairs, d over 2 downstairs. The crucial bit is the d halves. So this is how the mean square of this concentration, averaged over initial conditions, will diffusively decay. That's the difference in concentrations of A and B particles locally. All right. But C is a diffusive quantity, so we know more about it. C itself, C of x and t, will actually just be Gaussian distributed. So I can write down at any space-time point, I can write down this probability density, and it's going to be Gaussian with a width that's precisely this quantity, c squared averaged. Okay, so we actually know the Gaussian because all we needed to know for the Gaussian is the mean, that's 0, and the width, which we just computed. So that tells me I can go from this square averaged to the absolute value averaged. And I can do this at any space-time point by just using this distribution. This is like what you do in Maxwell-Boltzmann distribution. Same quantity, you want to know the mean velocity of a gas that's, the mean speed of a gas that's described by a Maxwell-Boltzmann distribution. So I would have this Gaussian, integrate the absolute value with this Gaussian. And of course, instead of going from minus infinity to infinity and worrying about the absolute value, I'm going to exploit the symmetry and just go from 0 to infinity and write down a factor of 2. Now that's easy because that's essentially just a derivative of this one aside from the factors 2c bar squared. So as for Maxwell-Boltzmann, you find this is square root of 2 over pi and this. What that tells me is I can get at the local excess, density excess of A and B particles, absolute value thereof, averaged over initial conditions by taking the square root of 2 over pi times that. Okay, and if you collect all the terms, which I'm not even attempting to do on the blackboard, the crucial thing you find is you get the square root of this, so it's minus d over 4. So that was the calculation. What does that tell us? If we're in more than 4 dimensions, it tells us that this density excess, the local density excess, so I have kind of, A-rich regions and I have B-rich regions. And if I look kind of locally on this difference, this decays faster than the mean field overall density decay 1 over t. So if I look at any local time, any of these kind of spatial homogeneities, any kind of species segregated areas, A and B, will decay faster away than the overall density. That means the system essentially remains happily mixed. Right? So any of these excesses go away fast, and the well-mixed conditions basically generates itself in larger than 4 dimensions, though. Right? So the system is basically well-mixed. Just say this decay is faster than 1 over t. So the system is well mixed. And that means the overall answer here is fine. This is what you would expect to happen. If I'm in less than 4 dimensions, I'm calling this a segregation characteristic dimension because it really is not a critical dimension in a randomization group sense. Then the local density excess decays slower than the overall density, which means you get species segregation into regions of filled with A particles, regions filled with B particles, and inside everything is inert. They just sit there and diffuse around and don't bother each other. And all the action is here at this reaction zone. But then, in order for them to meet and undergo further reaction, you have to have, this is really controlled by this density decay excess. So in this regime, you would expect that both particle densities decay as 1 over dt to the power d over 4. So in 2 dimensions, 1 over square root of t, not 1 over t. In 1 dimension, t to the 1/4. I was saying that this really is not a critical dimension in the randomization group sense, because indeed, you can really describe that, but that needs to be established. But you really can describe this in terms of these reaction diffusion equations, which is fine. So renormalization effects don't play a big role here. Any questions before I make some funny comments about this? Now beware, I was saying this is for generic initial conditions. Because you can cook up funny initial conditions, right? You can put all the A particles on one side, B particles on the other side, where you always have these fronts. For this to be consistent, one actually needs to also look at the scaling of these fronts, and you find that they actually sharpen as you go in time. So that works out too. But you can have funny initial conditions. Let's do this here. So let's look at a 1D chain, and we start out with correlated initial conditions. In the following sense, I'm having A particles, B particle, A particle, B particle, A particle, B particle. I could have empty sites in between, doesn't matter. but I need to have A's and B's alternatingly spaced. And I let them react with probability 1, so whenever they meet, they kill each other. Okay? Now, if you do that, what's happening? What's happening is that, maybe in some further time, this B kills that A, and that A kills that B. So let me write down another A here. And then I stare at the result. It doesn't matter if I kill an AB or BA pair, I still end up with AB, AB. So under the reaction kinetics, this ordering in one dimension will remain preserved. It just means whenever a particle meets a particle, they kill each other. Now, I told you the difference between A plus A to 0 and A plus B to 0 is what does not happen. Namely, that I have inert regions of A's and B's. With this setup, I can never have these inert regions. Reactions will always happen. That means, in this situation, it actually makes no sense to even distinguish A and B particles. You buy this? You look skeptical. Okay, because of this lining up on this 1D chain and the special topology in one dimension and the reaction probability 1, in this situation, the distinction between A and B just goes away because there is not anything happening. So the distinction A-B becomes meaningless. And what you get, therefore, is the 1 over T to the 1/2 decay, not species segregation. You just get the depletion physics. So you have to be a little careful, especially in one dimension, with initial conditions. Now you can generalize this, and just for sake, it's a fun story, let me quickly tell you about this. To do Q species annihilation. So I have two different species, Q different species, AI and AJ. I and J go from 1 to Q, so 1 is this, and let's say J is larger than I, and it goes up to Q. So whenever two different species meet, they can kill each other, and that's it. Okay? And of course, generically, you would have some density excess, and then you can worry about all these things. You might have different rates. Of course, the faster ones kill each other faster, so that generates a density excess and so on. So in a sense, the pathological, interesting scenario is when all the diffusion constants, reaction rates, and initial densities are equal. That's a special point. If that's not the case, the system kind of boils down to fewer and fewer species until you end up with either A plus B to 0 or something like that. All right, let's think about this one. Now there is two cases we know. We know Q equals 2, just talked about it. And you get segregation and 1 over T to the 1/4 decay in one dimension. And actually we know what happens if this is infinite. Because if I have infinitely many particles, then the chance for any of those to find a friend of the same species is basically 0. So it's only going to find different particles, in which case it's reacting. If it's reacting and never finds an inert particle, then that same argument as here applies. It really makes no sense to make a distinction. So the weird thing is that Q to infinity is really the single species limit. And you expect the T to the minus D over 2 decay. And you actually see that in simulations if you do. All right. The general answer with some work is, well, we need to worry about conservation laws, right? Conservation laws were generating this kind of segregation. It turns out that the situation Q equals 2 is actually special. It's the only one of these situations where you have a conservation law. On mean field level, you get more of those, but beyond the mean field level, only for pair annihilation do you have this conservation. Okay, so you don't get that otherwise. And so, no conservation law for Q larger than 3. And then you can argue with a little bit of work that the segregation characteristic dimension turns out to be 4 divided by q minus 1. So if q is 2, that's 4. If q is 3, we are in 2 dimensions. And for any larger values of q, there just isn't any segregation anymore in kind of typical physical dimension. And then you can also work out what the decay exponents are in 1 dimension. And you find that all these densities decay by a combination of 2 power laws, which reflect the 2 physical mechanisms we talked about. One is depletion zones. You always have the depletion effect. And kind of on top of this, and dominating, is desegregation decay. And the decay exponent there turns out to be q minus 1 over 2q. So if I look at that in the 2 limits we know, which is q equals 2, I'm happily getting 1/4, so we're in good shape. And if set q to infinity, I get 1/2, and these things actually coincide. This is slower than that one, so that's the leading behavior, but you always have a correction that comes from these depletion zones. So in that sense, we really understand pair annihilation fairly completely. But of course, you have any kind of funny combination of those, it's quite complex. So to show you that this isn't just theory land, there have been some really nice experiments that confirmed actually both of these scaling laws for a plus a to 0 and a plus b to 0. Let me just show you the one for a plus a to 0. And so, most prominently would like to have particles that you generate at sufficiently large initial density in an effectively one-dimensional system. And then you have them undergo chemical reactions. Okay? And the system for which that works best so far is actually you produce excitons on carbon nanotubes. Not maybe the first thing to think about, but that is where it works best. So carbon nanotubes, longish carbon nanotubes look like a one-dimensional system. You produce these excitons by shining a laser pulse onto them. And then what these excitons do, they move about roughly diffusively, and they can quench each other. When they find each other, they can actually go away. Something like a plus a to a, which is actually described by the same power laws. And so people have done that. So here's a plot where they then monitored in a log-log form versus time and on a scale of picoseconds in this experiment, this exciton density. And what you see, here's where they shine the laser pulse, and then things decay. Now initially, the exciton density decays as 1 over t. That's the reaction-limited, large density regime where they find each other happily and just go down. And then there's this crossover to 1 over square root of t, which in this experiment they could see over more than 1 decade, so it's quite convincing. They took the effective exponent of what they see here, and then this is the excitation regime. And you see you have some regime where you really see this exponent minus 1, exponent 1, which is direction limited regime, a fairly large crossover regime, and then here this diffusion limited regime. So very nice. And there are, not quite as good, but there are also nice experiments that show how this looks for a plus b to 0. Okay, so these were depletion zones, species segregation, as very characteristic and important correlation effects in diffusion-limited reactions. And they do show up in, as I said, biological systems too. Questions? Okay, at the very end, I would quickly like to walk you through non-equilibrium transitions in such reactions. And again, thanks to Sid's preparation, I can do this really quickly. So you might want of this again to think of this in the language of population dynamics. Or competing chemical reactions or whatever like this. So I'm going to look at particle decay. And by sheer luck, we actually use the same rate for this thing. I'm going to call that mu also. But luck ends at some point. I'm going to call the rate for this one sigma. because I'd like to call the rate for the annihilation lambda. So slight change in notation. So what's the mean field rate equation? Sid wrote similar things down, so very quickly, density changes, while we get density growth proportional to sigma, linear in the density, we get density decay with rate mu. So yesterday they looked like lambda minus mu. That's actually exact. That's a true statement if nothing else happens. Here comes an approximation for this process, and the approximation for that process is factorization of this two-point function. Okay. Then, as we heard yesterday, we know, of course, what happens for sigma less than mu. For sigma less than mu, all these things can do is die out and reach an absorbing an empty state. And so, of course, A of t is going to go as e to the minus mu minus sigma t. Because it's sufficiently low density, when this becomes in effect, I can forget this square term. So the rate here is mu minus sigma. And that rate will go away as mu equals sigma, which is then a special point. At mu equals sigma, we get only this squared thing into play. And we just saw that this is the algebraic decay, 1 over t, instead of this exponential decay. For sigma larger than mu, this grows, but the indefinite growth of the system will be cut off by this nonlinear process. This nonlinear process, a plus a to a, you could either think as direct competition, but also something that just fixes the total population number. So that's also resembling, kind of dynamically resembling some kind of finite, what biologists call carrying capacity. So finite resources or something like that. Anyhow, in this situation, we get that the density approaches a finite value, and that finite value is just sigma minus mu over lambda. Okay? And the approach is exponential. And the rate for that is sigma minus mu. All right. So if I now think of a spatially extended system, not this kind of one-dimensional nonlinear dynamics situation where I get a bifurcation at sigma equal to mu, but I look at this spatially extended in the thermodynamic limit. So infinitely many particles possibly there, but finite densities. Then this turns into a genuine non-equilibrium phase transition. Now, once this is a stochastic process, as Sid argued, of course, the absorbing state, when no particles are there, will always win. If I have no particles left, all my stochastic processes cease, and in a finite system, I'm going to reach this absorbing state with probability 1. But I'm going to do the infinite system limit first. And then I really have two different long-time states. And one of these is this one, with finite density that's active. And the other one where I get extinction. And I get a non-equilibrium phase transition that separates this active state from this absorbing and empty state. Now, once you have that established, you just write down critical exponents and the like with notation that's essentially stolen from equilibrium critical phenomena. For example, if I'm below the critical point in the active state, so I am at, what did I call that, sigma c, I would have this asymptotic density that grows as sigma minus sigma c to some order parameter exponent beta. And in mean field theory, that beta is 1. I can look at the critical point and look at the density decay at the critical point. Right, so this would be the analog of this one, which in this language tends to be called T to the minus alpha, which is not the specific heat, but we introduce this one. And we see from here that the mean field answer for that is alpha is 1, 2. Bless you. So the first step to go to spatially extended system, but still be essentially in the mean field limit, is to add to this equation some diffusion term. So we're changing our mean density to a local density field and write down what's called a reaction diffusion equation. Sid again has motivated that before. So let's do this. The time derivative becomes a partial in time. I'm adding per hand diffusive spreading. If these things spread ballistically, you have to write down something else. And then just keep these nonlinear terms. So we write this a little bit. So this start with a sigma minus mu plus d Laplacian a of x and t, and then have the minus lambda a of x and t squared. Okay? That's a space that describes spatial and temporal fluctuations. And I think as Sid explained, you can come up with solitron-like excitations for this that describe invasion fronts and the like. But it's still a mean field approximation. We've still applied a mass action factorization here. This is not the full story. We haven't really taken into account these are stochastic processes with internal reaction noise and with, or perhaps important spatio-temporal correlations. This thing here actually is the Fischer-Kolmogorov-Petrovsky-Petronov equation. So it's quite famous in this business of population dynamics. And of course, at low densities, that's generically what you have. Because you can think of the right-hand side as constructed in a kind of Landau expansion type philosophy as a power expansion of terms in, with respect to densities. So that's the first things you can write down, and that's why it generically shows up in wide context. But it's not the full fluctuating story yet. Before we get to that, let's just look at more of these critical exponents that I defined before that we can read off from this business. And so if I stare at this, of course something like eta would be 0, let's not worry about this, but with this Laplacian here, I can think of a correlation length. Just multiply the Laplacian with the length scale squared and call that the correlation length. That's a typical length scale. So the correlation length squared would be d divided by sigma minus mu. So this is d divided by sigma minus mu. And the absolute value depending on if you're in the active or empty state. But you see this grows as 1 over sigma minus sigma c to the power 1 over power nu, and in mean field that nu is 1/2, as it was for the time-dependent Ginzburg-Landau equation and the like. I can also look at a characteristic time scale, and that time scale is now afforded by looking at this relative to that, or looking at times and length scales. So this will scale as correlation length to the power c, and the time scale just goes as the square of the correlation length in mean field theory. It's diffusive, what else should it be? Okay, to that level. And then once you have that, you can write down a general scaling relation, as we did before, where this critical decay goes with the exponent beta over z nu. Beta is 1, z times nu is 1, so that's 1 divided by 1, which is 1. So you can do the same business. All right. Last 5 minutes. Let's try and construct a genuine macroscopic equation that takes into account fluctuations. So I'd like to write down a noisy version of that. but with the Ginsburg, Landau, or philosophy, where you expand terms. I'm going to do this in the language of, say, epidemic spreading. And so I'm going to look at something that's called the simple epidemic process. So I'm now thinking of this not as population dynamics, but maybe this is an infection that spreads in a population. So it spreads by infecting neighbors. It might be able to die out and such things. So it's a local stochastic process. So I'm infecting things locally, and it's governed by some density at x and t of locally infected individuals. I have diffusive spreading. That's what I need to invoke for this modeling. And I'm going to assume Markovian kinetics, which is implicit in all these, as I'm writing down a first-order time derivative, and nothing that invokes integrals over time or something like that, which would have memory effects. And most crucially, I want this to be an absorbing state. So I need to make sure that no reactions happen when the density is 0. That's true for this. But I also need to make sure that the noise vanishes when the infected density goes away, or in this language, the particle density. So let's construct a Langevin equation just phenomenologically that has these features. So diffusive spreading, some reaction functional that tells me how things interact non-linearly and linearly. But I want to make sure that as n goes to 0, nothing happens anymore in my process. So I'm just pulling out an overall factor n of x and t directly here, and then whatever else is left, as long as it doesn't go, is 1 over n. So if this is a function that is nice and smooth and can be Taylor expanded, this makes sure that the absorbing state condition is obeyed. And then I need to say something about my noise. Slightly symbolically, we want white noise, so there are my delta functions in x and t. There will be some noise functional, because the noise may depend on how many particles I have left in the system or the infected density. But I again want to ensure this goes away as I'm at the absorbing state. So I'm going to pull out an n there too. At this point, I do a Landau spirit expansion. And I would just write, say, this reaction functional as starting with a constant, let me call this d tau, plus something that goes with the density, plus perhaps the higher order terms. And likewise, I would expand this noise with a constant plus higher order terms. And then I put all this together, rescale a little, and I get a differential equation that I can write in this form. This d tau was my constant here, comes with a minus sign. I have my Laplacian. I have s. That's the linear term. Then I get minus us squared. That's the version of this rescaled. And noise. And in the noise correlations, the leading term is A2. After rescaling, I can call the BU. Comes with S and then these delta functions. So this is multiplicative noise. And that kind of stochastic differential equation you would expect to generically describe these active to absorbing phase transitions. Now this is a bit fishy, because that's an average over noise histories. This thing isn't averaged. So it's slightly symbolic. Okay, the way you can fix this is I could define theta to be square root of s theta prime. If I do this, this is just white noise, theta prime, but it would have the square root sitting here multiplicatively. So sometimes people call that square root multiplicative noise for that reason. But square roots aren't really analytic, so that has issues too. The way that's actually defined is in the path integral language, where everything just sits out in nice polynomials, and there's nothing wrong with this. Okay. Anyhow, you look at this, and you see that really this recovers this reaction diffusion equation, this Fisher-Kolmogorov PP equation, except that we have this multiplicative noise added. Okay? And what were the essential processes here? Well, it was things dying, things producing offspring, and coagulating. So if I think of some time direction, what happens is particles move, produce offspring, can coagulate, can produce offspring, can just spontaneously die. You look at these processes and follow them along in time, what you're generating is a directed percolation cluster. You see that? That's because, and then you can ask the question, what is the chance for this to span the entire system? Which is the epidemics just barely spreading? And therefore, the critical properties of directed percolation actually described by this dynamical equation. You can formally map that via field theory mappings, and again, John Cardy played an important role in this. You can map this onto what's called region field theory, which in turn is the description of critical directed percolation. So this dynamics or critical directed percolation is the generic description of such active to absorbing non-equilibrium phase transitions. Which brings me almost to an end. I just wanted to show you some experiments that confirm this very impressively on the context of magnetohydrodynamic turbulence. And so he and lots of friends, I don't know if I need to do the magic wiggling here again. So there's some kind of funny topological defects generated in this turbulent regime. And these funny topological defects play the role of particles here. And so at the critical point, they just barely go away, and you can analyze all kinds of different physical quantities with that. And I think they did about 6 or so, tested all kinds of scaling relations for directed percolation. Everything works out beautifully, and they do see the critical exponents of directed percolation. So here's some scaling plots. This is the critical density decay of these things. And so this is in the active phase, this is in the absorbing phase, this is the critical point, and they infer that slope, which is very close to the predictions of directed percolation. And these ones are rescaled functions here, so we can actually get the scaling functions. And you see this beautiful collapse working just out nicely. So it's one example where this is very prominently shown as actually being relevant in nature. There are other situations like that. Nigel Goldenfeld has recently argued that quite generically the onset of turbulence is actually described by the directed percolation class. So it's a very prominent universality class. And I'm glad I got here because I managed to actually show you the most important non-equilibrium universality classes in critical systems, which is model A. I argued that's equilibrium originally, but it survives non-equilibrium perturbations. It's things like the KPC-driven diffusive systems, Berger's equations, which are all related, and it's directed percolation. There are others, but those are the most prominent and unambiguously confirmed in experiment. And of course, there are these A plus A to 0 power laws, which are prominent too. All right, so thank you very much for your continued attention. And I didn't get to get my overtime to 0, but at least I kept it within 3 minutes.